Hi there. I would like to start off this new series of online tutorials by discussing the chemistry of pi systems. I have made a dedicated playlist for organic chemistry tutorials and also will do the same for physical and inorganic chemistries. These videos will cover the notes given in my lecture at university and also uncover blurred areas which were not covered. The main three courses, organic, inorganic, and physical chemistry, are divided into three sections which you can conveniently find in my video playlist. These courses will be individually divided into main topics and depending on the content material and the depth I go. The main topics will also be divided into subtopics. For this main topic, chemistry of pi systems, I have divided this topic into a few subtopics because developing a strong base in pi systems is essential to understanding aromatic chemistry. In this subtopic, we will look at pi bonding, pi electrons, some hybridization, and valence bond theory. To begin, I would like to introduce the pi bond, as we might think to know as a carbon-carbon double bond. Pi bonds are weak covalent bonds formed by the sideways overlap of p orbitals. Pi bonds have less overlap than sigma bonds because of their parallel orientation overlap. Therefore, they are generally weaker than sigma bonds. Please remember, sigma bonds are head-on overlap, and pi bonds are always side-to-side parallel overlap. Moving on to valence bond theory. When we refer to an electron, we use the term electron pair. This is because an electron has two spins. Therefore, it is an electron pair. You can also use the term two electrons to describe an electron pair. I will use the term one electron to describe the half-spin electron and two electrons for the electron pair. Covalent bonds, according to valence bond theory, are formed between the two atoms by the overlap of half-filled valence atomic orbitals of each atom containing one unpaired electron. In general chemistry, the formation of electron pairs is much more energetically favorable, either in the form of a covalent bond or as a non-bonding electron lone pair. Unpaired valence electrons are usually reactive, and hence explain why atoms favor bonds with other atoms to form molecules. Unpaired valence electron is one electron. It occupies an orbital singly by itself with only one spin. In organic chemistry, unpaired valence electrons only occur briefly during a reaction forming a radical. We draw curly arrows in reaction mechanisms to illustrate the movement of electrons. The appropriate way to draw a mechanism is to use the arrows correctly. Full arrows will represent the movement of two electrons, and half curly arrows to represent the movement of one unpaired valence electron. If using half arrows, it will help to draw a dot on the electron accepting atom to represent that it has an unpaired valence electron. As mentioned earlier, these radicals are very reactive and will favour to form a covalent bond very quickly because the radical will occupy the empty orbital singly. Moving on to hybridization. The process of hybridization is the excitation of the paired electron in the s orbital over to the p orbital, and the combination of both orbitals to form a mixture of new orbitals called hybrid orbitals. For the formation of ethene, we will require a sigma bond between the two carbon atoms and also a pi bond to form the double bond. This is achieved by hybridizing both of the carbon atoms to form 3 new sp2 hybrid orbitals. The reason why we need to hybridize the carbon to sp2 is because if we look at the ground state of carbon, this one here, we only have 2 unpaired valence electrons in the 2px and the 2py orbital. This will only form 2 bonds, since we need to form 2 sigma bonds with hydrogen and another sigma bond with the carbon, a parallel pi bond with the other carbon atom is required. For this, sp2 hybridization will be necessary. A good example of a pi bond is the ethene molecule. Ethene has a double bond between the 2 carbons. This double bond consists of 1 sigma bond and 1 pi bond. The carbon on ethene is sp2 hybridized. Let's try and get to focus the camera back on there. The sp2 orbital is formed from the hybridization of the 2s orbital with 2 of the 3 2p orbitals. This is the 2s orbital. The electron moves from this 2s orbital over to the empty 2pz orbital. And then these 3 orbitals here combine to form sp2 hybrid orbitals. However, this remaining p orbital remains unhybridized. The reason for this is because this orbital here is used for the pi bonding. So, sp2 orbital is formed the hybridization of the 2s orbital with 2 of the 3 2p orbitals. The ground state of carbon, which is the lower energy state, has electron configuration 1s2, 2s2, and 2p2. However, more accurately, this can be described as 1s2, 2s2, 2px1, and 2py1. This is because the p orbitals have 3 different shapes, which is x, y, and z. As you can see, this is the ground state of carbon here. If we draw it on the orbitals individually. As you can see here, we have 2 valence electrons in the p orbitals. Now, the reason why carbon doesn't exist on its own as a singular element is because of these 2 valence electrons occupying the orbitals by themselves. These are radicals, and they will form covalent bonds extremely quickly. So, hence, carbon element on its own is very reactive. The core 1s2 orbital is almost never involved in bonding. The spherical 2s2 orbital is occupied by a spin-paired electron. The dumbbell shape of the 2p orbital is divided into 3 atomic p orbitals. And there is an unpaired valence electron in the x and the y p orbital. The 2pz orbital occupies no electrons and is empty. The carbon on ethene will undergo sp2 hybridization because carbon will form the pi bond. In more detail, the 2s2 orbital will be excited, so a valence electron will move from the 2s2 orbital over to the empty 2pz orbital. Now we have 4 unpaired valence electrons occupying an orbital each. This 2s2 orbital here will combine with the 2px and 2py orbital to form 3 new sp2 hybrid orbitals. A good way to remember your sp2 and 3 hybridization is the 2 stands for the number of orbitals it combines with. So in this case, sp2 here combines with the px and the py orbital. In sp3 hybridization, the 2s orbital will still follow option this number 1 here, with the electron moving over, exciting over to the 2pz orbital. However, in sp3 hybridization, 3 of the orbitals will hybridize and combine and form 4 new sp3 orbitals. So sp3 is combining with 3 p orbitals, sp2 is combining with 2 p orbitals, and sp hybridization will combine with only 1 of the p orbital. The difference between sp3, sp2 and sp1 is sp3 will form 4 new sp3 orbitals, so there will be no p orbitals available. sp2 hybridization will combine and form 3 sp2 hybrid orbitals and 1 2pz unhybridized orbital. For sp hybridization, we will form 2 sp hybrid orbitals and we'll have unhybridized 2py and 2pz orbitals. So we have 2 orbitals available, 2p orbitals available. Therefore, sp3 hybridization will not undergo pi bonding. This is because there are no empty p orbitals or no p orbitals available for pi electrons. sp2 has 1 unhybridized p orbital, so it can undergo a sigma bond and a pi bond here using this p orbital. So parallel orientation here. And for the ethene molecule, you'll have 2 p orbitals available for pi bonding, and you also have the same one, sigma bond here. The reason why atoms need to hybridize and form new hybrid orbitals is because the formation of new hybridized hybrid orbitals will increase orbital interaction and solve difficulties of bond formation in terms of orbital overlap symmetry and the differences in orbital energies. These three new sp2 hybrid orbitals will have 1/3 s orbital character and 2/3 p orbital character. This is because out of the total 3 sp2 hybrid orbitals, one is originally from the 2s orbital, and the remaining two are from the 2p orbital. Now, for demonstration purposes, I have two sp2 hybridized carbon atoms. This is the sp2 hybridized carbon. This is the hydrogen. This is the sp orbital here, and this blue one here is the 2pz orbital. Now I also have the same for this side as well. The blue is the p orbital and the green is the sigma orbital. When these sp2 hybridized carbon atoms approach each other, they form a strong sigma bond by sp2 head-on overlap. Right here. At the same time, the unhybridized 2pz orbital interact by a sideways overlap to form a second pi bond, which is this one here. This is the pi bond formation, and this here is the sigma bond formation, the green ones. And the white ones are the sigma bonded to hydrogen here. The combination of sp2 sp2 sigma overlap and 2pz 2pz pi sideways overlap results in a net sharing of 2 electron pairs . 1, 2. And the formation of a carbon-carbon double bond. This combination here will then equal to this. Now I have drawn here diagrams to illustrate the formation of ethene more clearly. So here we have the 1s2, and then we have the 3 sp2 hybrid orbitals, and then we have the unhybridized remaining at 2pz orbital. Now this 2pz orbital combines with carbon to form the pi bond, as we just mentioned here. The blue one here is the unhybridized 2pz orbital, which combines with the other unhybridized 2pz orbital, which can also be illustrated on this lower diagram here. You have the carbon 1 and carbon 2. So we have 3 sp hybrid orbitals on the carbon, and then we also have the unhybridized 2pz orbital, and that is pi bonded to the other carbon, and so this here forms a bond, the pi bond, and that is the 2 blue ones coming together. And then the remaining sp2 hybrid orbitals will sigma bond because they can only sigma bond. Hybrid orbitals can't form pi bonds. Only unhybridized orbitals can form pi bonds. So the remaining sp hybrid orbitals will sigma bond to the hydrogen, and then will sigma bond to the other hydrogen. So we'll sigma bond 2 hydrogens, 1, 2. And then we'll sigma bond to the other carbon, which is the green one here, sigma bond into this other green one here. And as we just mentioned, the parallel overlap there with the pi bond for the formation of ethene. And the use of this diagram here can also be applied to other molecular diagrams. For myself, I found this one more easier than to use the molecular orbital theory, as I can lay out the molecular orbitals more clearly using the outermost electronic energy shells. So here we go, that's the ethene there. There's the sigma bond and the parallel bond. Now for something more difficult, for the formation of ethyne, which is the triple bond, both of the carbons form sp hybrid orbitals. The electron paired in the 2ps orbital, the 2s2 orbital here, so the electron paired in the 2s2 orbital will be excited as a single electron over to the 2pz orbital, which is also the same for sp2 hybridization, so it's the same process there. However, the difference between sp and sp2 hybridization is the final mixing and combining of the s and p orbital, which we discussed earlier. For sp hybridization, the 2s orbital will combine with only the 2px orbital here, and form a mixture of only 2 new sp hybrid orbitals. So remember, sp hybridization will combine with only 1, and sp2 will stand for 2, so combine with 2. sp3 will combine with 3 to form sp3. The reason why sp hybridization is required is due to right symmetry required to form the new bonds. The sp orbital will overlap head-on with the other carbon to form the sigma bond between the 2 nuclei, and the remaining sp orbital will head-on overlap with the hydrogen, forming a covalent sigma bond. The remaining unhybridized 2py and 2pz orbitals will sideways overlap with the other carbon, 2py and 2pz, to form 2 new perpendicular pi molecular orbitals. So these new p orbitals formed are perpendicular to each other. like this, 90-degree angles to each other. The sp hybrid orbitals have half s character and half p character, because there's half of there and half over there. And they form a linear 180-degree carbon skeleton. 180 degree between two hydrogens here. Ethyne has 3 paired electrons holding the two carbons together. So you've got 3 paired electrons, so that's a total of 6 electrons being shared in here. Therefore, it has a stronger attracting force compared to ethene, so it has a shorter bond length and has higher energy required to break this triple bond. As you can see, there's more strain in this bond here, so the more electrons attracting each other, so it's much more stronger. As you can also physically see, it's much more stronger compared to ethene, which this is solid. This is because of the perpendicular p orbitals which are formed here. So you have 2 electrons in this plane and 2 electrons in this plane being shared. So it has extra locking feature here. However, it is important to note that it takes less energy to break the carbon-carbon pi bond than the carbon-carbon sigma bond, due to less effective parallel sideways overlap. As I first mentioned at the beginning of this video, I stated that the pi bond is weaker than sigma bond because of parallel orientation, therefore it has less overlap. Another important note is ethene and ethyne are actually not formed by bringing together 2 carbon atoms which individually hybridize their atomic orbitals and combine together. Hybridization is a mere tool to help rationalize shapes of molecular orbitals. In both the double bond and triple bond, there will be electron density occupied above and below the line drawn between the 2 carbon nuclei. Pi bonds are more diffuse than sigma bonds because the p orbital are overlapped sideways, not head-on. Hence, the electrons in pi bonds are referred to as pi electrons. Molecules joined by a pi bond cannot rotate around the bond without breaking the pi bond. No free rotation here, and no free rotation there. For us to make a ethane molecule quickly, then that we have a degree of free rotation here. The consequence of this locking effect is that there will be 2 isomers, cis or Z, and trans, known as E-alkene. illustrate this here for more convenience. One way to break this pi bond would be to promote an electron from the pi bonding orbital to the pi anti-bonding orbital, and hence this will cause no bonding. Another way to break the bond is to use electromagnetic radiation of the correct energy, such as ultraviolet light, to promote and excite the electron in the pi molecular orbital to the pi anti-bonding molecular orbital. Therefore, no overall pi bonding, and free rotation about the actual sigma bond is now possible because there is only one bond, the sigma bond. So we have now a radical formation here. The unpaired electron in the anti-bonding pi molecular orbital will come back down from its excited state, and then a new pi bond will be formed. This time, since free rotation has occurred during the excited state, it's possible for two isomers to be formed. Now to finish off with the summary. Pi electrons occupy p orbitals to form pi bonds. A double bond has one pi bond which occupies two pi electrons. A triple bond has two pi bonds which occupies four pi electrons. A single electron is called an unpaired valence electron. They form new bonds when they are moved to a different atom when using the half curly arrow. Two electrons are called non-bonding lone pairs, and they can be transferred using a double-headed arrow. One electron is called a valence electron, and they can be transferred using the half-headed arrow. Hybridization involves exciting an electron to a higher energy, i.e. the p orbital, and involves combining the s orbital to the p orbital to form new hybrid orbitals. sp3 hybridization forms no p orbital. sp2 hybridization forms one pz orbital, and sp hybridization forms a pz and a py orbital. As a rule of thumb, pi electrons can maneuver easily because they are not engaged in bonding. Unshared electron lone pairs can be moved easily because they too are not engaged in bonding. Hence, most curly arrows will always, or mostly always, originate from pi electrons or lone pairs, and they will most likely point towards atoms with higher electronegativity and atoms with electropositive charges. Thank you for watching.